And microphone is also on. And if not, then the world will shout out to me and say something is wrong. Good. So yeah, welcome. So this is, before I start, a little bit about the course. So this is the last in-person lecture for about 4 weeks or so. So the next 4 weeks we have guest lecturers. And let me just give you the names, if you can look them up if you want. So we have Anna Marciniak-Chokra. Nobody can spell her name. Marciniak-Chokra. She's from University of Heidelberg, and she's currently one of the editors-in-chief of the Journal of Mass Biology. And she will talk about leukemia modeling. So this will then be a little bit continuation of what Natalia Komarova did about cell lineages, about feedbacks, and then here in particular for leukemia. After Anna, we have Mark Chaplain. Mark Chaplain was here. He's from St. Andrews University in Scotland, and he is really a pioneer in cancer modeling. He might have been one of the first 4 or 5 people who ever did cancer modeling, like 30 or 40 years ago. So he will talk about angiogenesis. So maybe I'll write this here as well. Leukemia, this will be angiogenesis. Who knows what that is?
Like tumor growth paradox, like that. The growth of tumor because this.
No, this is not this. This is not the tumor growth paradox. Angiogenesis. What is angiogenesis? Somebody online.
It's when you get new blood cells. New blood vessels, new blood supply for the tumor as it
Very
grows.
good. Yes, exactly, Amy. Wonderful. Thank you. Right. So it's the development of blood supply or the growth of blood supply into the tumor. And then Mark will use the kind of reaction diffusion equations we studied today. So we certainly need to get a little bit more information there. Then we have Luigi Preziosi from University of Torino, and he will talk about tissue mechanics. Now, if we talk about cancers in tissues, right, for example, a brain tumor, it will also have mechanical effects. It will deform the brain, right, or it will grow towards the skull and produce pressure and headaches and strain and stress and these kind of things. And so Luigi is an absolute expert in this mechanical modeling of tumor growth. And so he will tell us a little bit about this. So I was just saying the next 4 weeks will be guest lectures. So this will all be online. Yeah, and I'm just going through the names who do this. And now Mark and Luigi are currently writing a new textbook on mathematics of cancer modeling. It's already an 800-page manuscript, which covers essentially everything I did and much, much more. So I heard about this when I prepared for this lecture, and I asked them, can I have your text? But it was not ready yet, so I had to use my own notes. But anyway, so the book is coming of those 2 experts. This will be a blast. Okay, and then we have Thomas Yanquilo. He is from University of Texas, and he is leading the world-leading group in glioma modeling, so in brain cancer modeling. And he will tell us how to use all these different images, like the MRI images and PET scan images and FLAIR images and what have you, to diagnose and also to treat glioma, and treatment typically with radiation or with surgery and so on. So this then it will be much more data oriented. We will see the data they use, how to fit models to data, how to inform models on the data, etc. Whereas the other 3 is probably more theoretical. So something to look forward to. And then after all this comes the real highlight, which is myself. Yeah, you thought you cannot increase this, but of course you can. So I give them the last lectures in the course until we finish. All right. So let's come back to the reaction diffusion equation. So I need to cover some ground here today. I'm one lecture behind. Today, I actually wanted to do stochastic processes and tumor control probability, but we were lucky, at least people at Fields. We had a talk yesterday by Vova Vinogradov about tumor control probability and stochastic modeling. So it's maybe not too bad that I don't have time to do it here. But I definitely want to do reaction diffusion. So let's go back to the model we have here. So U is some population density, for example, cancer cells. J is a population flux, and let's say a bit more about this today. And then F was a production or decay term, so it could be cell division or it could be cell kill due to a treatment, for example, or whatever reasons they are. I forgot to explain last time what the divergence is, so I think it would be fair just to say this, because not everybody might be familiar with these things. So the flux is a vector. It has components J1, J2, up to Jn. And then the divergence is the sum of the derivatives of, well, let's write this down. So this d by dxi of the ith component of this vector j. Okay, and then we sum I is 1 to n. So it's a sum of all the first derivatives of the components of I, where the ith component is differentiated by xi. So yeah, this is called divergence. So what we like to have here in the arrow thing is an equation for U alone. And now we have U and J. So this is a little bit too much. Either we need an equation for J, or we need to get rid of the J and get something with U. So we need original and great ideas. So what is a flux J of xt? And then we could ask the smart people in the Zoom and the smart people in the room, or we could ask the smart people in history and see what they did before us. So let's this time let's ask the people in history. And I would say the most famous choice or the most important choice is called Fickian law. Fickian law, which was introduced by Fick. Fick was a German, I think, physician or something. So Fickian law for diffusion. And this says that the flux is proportional to the negative gradient of the population. Let me write this down. So J of xt is a constant. We will turn out the diffusion constant times gradient of U of x and t. Right, so this upside down triangle is a gradient. Maybe I do this as well just quickly. And this makes a vector, d of dx1 of U, d by dx2 of U, and so on, d by dxn of U. So it's the gradient. So we have a scalar quantity U, population density, and we make it into a vector by taking all the derivatives. And then J is a vector too, right? So then the type matches. So the vector is proportional to a vector, so that's great. But now, what does a gradient describe? Okay, so this is a question for you guys. I think the old guys in history knew what a gradient describes, but what does a gradient tell us? How a function changes, very good. It's like the derivative in higher dimensional space. But it's also a vector. Which direction does this vector point to?
Tangent to the trajectory.
It's tangent to the trajectory if you go uphill. So it tells us the direction of steepest increase. That's what the gradient does. It tells us the way uphill. And if you want to go downhill, you go to the negative gradient. Okay, and this is Fick's law, right? So Fickian law. So you go down the gradient of U. So for example, if U is something like this, U of xt, then here at this point, the gradient is up to the right. So the Fickian flux would be downhill, J. And on this side here, the flux would be downhill this way. Okay, and this describes the biology very nicely. So the species try to avoid to clump up too much, so it likes to spread out as much as it can. Okay, and so that's a mechanism to spread out locally. Okay. So this is X. I didn't plot time dependence here, but this is how Fickian law works. Now, if you talk to, for example, Luigi Preziosi, I mentioned here, he comes actually from thermodynamics, and he would know Fourier's law. And let's look at Fourier's law. And Fourier's law, you are concerned about heat conduction. So then U would be a temperature profile. And of course, temperature flows from hot to cold, right? So then if you have a profile like I plotted here, it would get colder on top and it would get warmer on the sides. So the Fourier law is J of xt equals minus G gradient U. Oh, wow, that's cool. So they actually came up with the same law in totally different applications. One is for chemistry and the other is for thermodynamics. And this is also a reason why this is so important. We can look at unbiased random walk, which I did in the last lecture. I talked about these random walks. From this random walk, we can also derive a flux. I haven't done this, but it is not difficult. And if we do this, we find this formula is minus D gradient U of X and T. So you see where this is going. So it's really more like a universal law than a specific choice. And that's why it's so important. Okay. One more thing, Cattaneo was an Italian mathematician. He came up with his own law, which is not of this form. It is epsilon jt plus d gradient of u equals minus j. So this is actually a differential equation for j. Jt means the time derivative. If you set the epsilon to 0 just in your mind, right, then you're back at Fickian's law. But this epsilon creates like a delay. So it takes a little bit of time for the flux to adjust to the gradient. So this is used too, just to show you there are other choices, but we will not bother with this in this lecture for sure. So we go with Fickian or Fourier or unbiased random walk law, which are all the same. Okay, so let's put this in then. So we have J is minus D gradient U, which we want to put into the divergence now. Okay, so we need to worry about divergence of a gradient. What is this? So then du by dt, then how does I wrote this? I have to get a minus sign, so I move it to the other side. Then this minus sign goes away. D divergence of gradient of U plus f of u. Okay, so I moved the terms over and I take care of the minus signs. So what is diff grad? Where are my theoretical physics experts? Divergence of gradient. Laplace, yes. Very good. So diff grad u is actually Laplace u. And I write this out as well, which is just the sum of all second order derivatives. 1 square of u plus d square by the x2 square of u plus blah, 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 plus d square by the xn square u. So that's the sum of all second order derivatives. But if you take the gradient u as a vector and vector multiplied with the divergence, which is a vector of derivatives, and use the rules here, you get exactly this. All right, so then insert page. So then we get du by dt, du by dt equals d Laplace u plus f of u. And this is the famous reaction diffusion equation I was looking for. Equation, nice. So let's have some fun. This is a common famous model for also for cancer modeling, also in ecology, shows up many times. So there are two important problems I like to study here. And one is called the critical domain size problem. Yeah. And the other one is called the traveling wave problem. If you have been attending the workshops over the last month, you will have heard about traveling wave problem all the time, right? They use it to estimate the invasion of a glioma or the invasion of a cancer in a tissue, etc. So the traveling wave problem is directly relevant to what we do. The critical domain size problem also, because the critical domain size problem is the question, how large does an environment have to be to support a population? For cancer, meaning what kind of resources or how much space do you need for a cancer to grow? If the environment is too hostile, the cancer might actually not grow, which is a good thing. So, okay, let's start with number one, critical domain size problem. I have a nice picture here, which is not cancer, but I plotted anyway. So, so this is a little bunny here. Yeah, this bunny is nice enough. And there's a little palm tree. Oh God. I said I wanted to cover material today, but anyways. So that's a tree, and this is in an island. So there are hostile conditions, and it's very hostile. So here are sharks, which are swimming around. And every bunny which gets too close to the boundary will be eaten by sharks. So then the question is, how large does the island have to be to support a bunny or a bunny population? If you make it too small, well, they will eventually get too close to the water and be eaten. So you need a certain amount of space and a certain amount of resources, etc. So that's the question. Yeah.
The bunny is not a squirrel, it cannot climb the tree.
It cannot climb the tree either, exactly. But I mean, for squirrels, you would have a similar question. Yeah, so how large? Why does this do this? Okay. How large does the habitat have to be to support a population? And we will answer this with mathematical models today. So this is important, of course, for ecology, if you want to conserve particles. For example, there are something like marine protected areas. These are areas in the marine ecosystem where fishing is not allowed. And so species are safe. And then you can ask the question, okay, how large does this marine protected area have to be efficient to support this population? It's important for farming, right? You want to have a thriving population for your herd of sheep or for your herd of cow, for example. It's important for pest control. And of course, in our case, it's also important for cancer. So if you can reduce the habitat for possible habitat for cancer, then you would do that. And you want to know how small you have to make it. Okay, to study this, we use the famous Fisher KPP equation. Fisher KPP. KPP stands for Kolmogorov-Piskunov-Petrovsky, Russian mathematicians. And the equation is this, so du by dt, now I use the index notation, duxx, so second spatial derivative, plus mu u 1 minus u. Let's compare this back to our a more general equation, which I just had earlier. So here I had the Laplacian and I had an f. Laplacian in one dimension is just the second derivative. And the f I use what? Who knows what this f is? A logistic, right? That's a logistic equation. And we have seen this in the modeling before. So again, a very natural choice to do. And then we do this on a finite domain. Which is a 0L, so maybe just an interval of 0L. So now we need boundary conditions. And there are three typical boundary conditions, which I just like to introduce. So first is homogeneous Dirichlet boundary conditions. Homogeneous Dirichlet boundary conditions, which means U at the boundary is 0 and at the other boundary is also 0. The second class would be homogeneous Neumann boundary conditions. Boundary conditions, which is that the flux is 0. They're also called no flux boundary condition. Okay, flux we just talked about. My flux is my J, and J was the negative gradient of U. So which means the gradient of U is 0 on the boundary. And written in turn, so we write this as Ux is 0 and Ux at L and T is also 0, okay? So, well, we should write minus Ux is 0 and minus Ux at L is 0, but 0 has no sign, so it doesn't care about this. Okay, and then there are Robin conditions. And they are mixed. So they're mixed boundary conditions. So for example, you could have alpha U plus beta Ux is 0 on X is 0, for example. Something like this, with coefficients alpha and beta. And if you said alpha is 0 and beta is 1, you're back in the Neumann case. If you said beta is 0, you're back in the Dirichlet case. Okay, so that's just a mixture of the two previous ones. Okay, talking about boundary conditions is actually sometimes confusing for people. So I developed my own rule of thumb. I call it the Hillen's rule of thumb. So let's learn about this, which is never spelled out in any book. So, but I find it useful. Hillen's rule of thumb says that the number of side conditions you need is equal to the number of highest order derivatives you have. So, number of side conditions equals number of highest order derivatives. So this is what you need to get a well-defined PDE or a well-defined problem. So let's see how this works. So if we have a reaction diffusion equation, we have UT equals D UXX. Yeah, let's use Fisher KPP. So how many conditions do we need? We have a time derivative is order 1. So we need one time type condition. What could that be?
UXX.
And UXX, we need two conditions for space. So one for time and two for space. Right, so the time like initial, it's the initial condition. So one initial condition. So that would be something like U at X and 0 is a function, maybe phi of X is given. And for space, we have two boundary conditions. for example, for Neumann conditions, you can still see on the top here are two conditions, right? Or as I had Dirichlet, I had two conditions, one on the left and one on the right. So maybe as above. Neumann or Dirichlet or Robin. So there need to be two, and there are two. Okay, let's play this once more for the wave equation. So the wave equation would be something like UTT equals C square UXX plus UYY. I make this now two-dimensional on a box. So this would be a square drum, a vibrating membrane on a square. So a square drum. So how many boundary conditions do we need? 4 for the boundary,
Oh, 2 for the time,
2 for the time.
2 for the space.
Okay, but we need to differentiate between x and y derivatives. So we need 2 for x and 2 for y and 2 for t.
6.
So we need 6. Right? And so for time, for the wave equation, if you're familiar with this, you usually give an initial, what do you call this? If you take a string and you pull it, dislocation, initial dislocation, but also an initial velocity. Well, for a drum, right, you hit it with a velocity. So, so time initial condition would be initial displacement plus initial velocity. So you need two initial conditions. And for the 4 spatial boundary conditions, well, these are the 4, right? We have 4 sides. So we need conditions there. 4 sides. Yeah, and then you have your 6 conditions together. So this rule always works, unless you prove me wrong. But good. So let's come to the critical domain size problem. So now we use Dirichlet conditions. So we have an interval from 0 to L. And we have U at 0t is 0. So the sharks will eat everything. And if you get to the boundary, even if you get onto the boundary, you will already be eaten or killed or whatever happens there. So this is a Dirichlet. Now, there are 3 ways to mathematically formulate the problem, and they're all equivalent. And I want to list them, and then I probably do 2 or at least 1. So the first question is, how large does L have to be to support a population? Okay. But secondly, we can ask, what is the size so that the 0 solution is unstable? So the 0 solution is always possible. You can always have an empty island. But you want it to be unstable so that something can grow. So how large L such that U identical 0 is unstable? Now this sounds like a mathematical question we can study, because we have looked at stability before, stability of fixed points. We can do linearization and eigenvalues and these kind of things. And 3 would be, if a population now grows, it will form like a steady state, maybe of this form here. So we can ask the question, do these steady states exist? So how large L such that a non-trivial steady state exists? Okay, and so I do the third one first. This seems to be mathematically the most intuitive. So I'm looking for steady state solutions of my Fisher KPP equation. which I can fit into this domain from 0 to L, and is not 0. Let's do 3. Yeah. And as I say, one can show that all 3 are equivalent. So then eventually you can choose what you want to do. Now, good. So let's do 3. Steady state means UT is 0. And then we go back to Fisher KPP. Which one? This one. If UT is 0, then we get something for the second derivative of with respect to space. And I move this uxx then to the other side and divide by d. Okay, and so then we get this here. We get uxx equals minus mu divided by d u1 minus u. So this all of a sudden is just a second order ODE. It is a nonlinear ODE. But nevertheless, it's a second order ODE, which we can solve by phase plane analysis. So I introduce V to be U prime. And then I can write this as a system. Oh yeah. And I use the prime now for the spatial derivative. So then I have U prime is V. And V prime is U double prime is minus mu divided by D U1 minus U. So we get a system now of our variable U and some helper variable V, which is the gradient of U or the derivative of U. So let's give this a star. So now we analyze star. And this we do by the standard thing. So we look for equilibria, linearize, eigenvalues, eigenvectors, all that stuff. So let's analyze star. Okay, here we go. Equilibria, we have a point 0, 0. It's an equilibrium, right? And then you can linearize to the Jacobian, find the eigenvalues. This is stuff we discussed. And you find this is a linear center with eigenvalues. Lambda 1 and 2 are plus minus I root of mu divided by D. I think you are fine if I skip the details, right? This is, hopefully this is pretty clear what I'm doing. And then we have another fixed point, which is P2 is 1, 0. And this turns out to be a saddle point. And I will put this together graphically just in a second. Okay. But we find P1 is a center. So center is not hyperbolic. And this is something we discussed at some point. If it's not hyperbolic, we are in a mess because we don't know if the nonlinear system is also a center or not. So we need something like a Lyapunov function or a Hamiltonian function or some other information. And we are lucky we have this here too. We have a Hamiltonian function. Which is h of u and v is 1/2 v square plus mu over d of u square half minus mu over d cubed. And this works so well, yeah, I can move it just a little bit because the u equation in star only depends on v, and the v equation only depends on u. So then you can essentially integrate these things to get a Hamiltonian. And if we have a Hamiltonian, we know a center is a center. So this is good. So then I write this down here as well. So dh by dv gives us u prime, and dh by du gives us minus v prime. That is the definition of a Hamiltonian function. You can check it out. This works just wonderfully. Okay, and now I can put this over the phase portrait. Let's see, this is going to be an interesting picture. I don't know how good you are in plotting 3D. I try my best. So I want to have U here and V here and the Hamiltonian here. And now I plot the Hamiltonian in a different color. Maybe the light blue will work. So I do it. It's going to be interesting like this. And like this. Okay. And then it goes down here to the bottom, comes up a little bit and goes down again. So they should see this like a bowl here. Oh God, does this work? You get an idea how this looks like? Yeah, I could. You could. It's a little bit like a slide on a playground, where you slide out here to the right. Important is that it has a local minimum here. So there's a little minimum, a dimple, and then it goes further down there. And then the level sets are solutions. Okay, now this curve doesn't work here. No, I'm messing it up. Let's see. So here we have actually circles going around. Yeah, so this is better. So orbits are closed curves. So let me plot this outline now in the proper phase portrait. Going back to blue. Now I look on this at this from top. I plot U and V. Now I know here I have a circle. Here I have another fixed point, which is a saddle point, and it will go around like this. It goes out this way. It comes in this way. And here it goes around like that and like that. And now orbits here, they do this. Orbits here, they do that. Orbits here, they go like this. So this is the two-dimensional phase portrait of the little model which I just derived earlier, phase plane. Okay, so now where are our solutions? So what did we do? Where are our solutions? Let's look at the Dirichlet problem. What was the Dirichlet problem? And I want to use a different color, maybe red. So Dirichlet. So Dirichlet says U at 0t is 0 and U at LT is 0. So where is this in my graph? Well, U at 0 is on the v-axis. All along the v-axis, U is equal to 0, right? So we need an orbit which starts on that axis and comes back to this axis. So we need an orbit maybe of this type, starting here, going around, ending here. So the red orbit, as indicated, is a possible solution for the Dirichlet problem. And there are many, right? You can be closer to the center, closer to the origin, or you can be further away. Maybe you are all the way over here, curve around, come back. So there are many, many candidates for possible solutions. Before I discuss this further, let's do this for Neumann condition. Neumann, do this in green. Do you have enough colors? And so we have now a Neumann ux is 0 and ux has become v, right? That's our new variable v. So this would be v at 0t is 0 and v at lt is 0. So let's do the same thought experiment. So where can this be? So v is 0. V is 0 on the u-axis. Right, so we need to start and we need to end on the u-axis. So where can this happen? Maybe I ask you now. So where? Hmm? So yeah, right. I think you have maybe this in mind. So this one here, right, would be a possibility. Or you go down below, this is another possibility. Or you go around 5 times, it's also a possibility. So these would be the Neumann solutions. Or, yeah, periodic, right? It's periodic. Or we could have this one point here, which is a fixed point, but it is still starting at this axis and ending at this axis as a possible solution. However, these green ones, these green circles are useless because they become negative, right? U is a population density, and here we become negative in the green, which we can't have. We can't have negative populations. So these green circles around the origin are not possible. The only possible way for the Neumann would be 1. So only U is identical 1 and V is identical 0 is the only solution for the Neumann problem. Okay, but the Neumann problem was boring because there's no sharks. So we want to go to the Dirichlet problem and see if we can find a condition for the length L. Okay. So let's maybe plot this just once more, and I go to red to indicate that we are in the Dirichlet case, but I make it bigger. So I want to make it very big. Okay. So this is the inner region, right? And we found a possible Dirichlet condition solution like this. Now this solution needs the length L. And L is the the coordinate for all this phase portrait is the spatial coordinate x. So then the length L is actually the time you need to come from here to make a half circle around the origin. The time you need in the phase portrait corresponds to the length L. And yeah, and now we ask the question, what happens if we get closer and closer to this saddle point here? If we go around very close and then come around, what happens to the length of the orbit? Can somebody tell me what happens to the length of the orbit? Let's maybe call this orbit B, and this orbit we call A. So like maybe in the limit, as you get closer and closer to 1, what happens to the length of this orbit? It's maximal, it's more than maximal, it's infinite. So the orbit needs an infinite time to curve around this steady state 1. And if it gets super close, it takes forever. So so time, no, length of B is kind of infinity, okay? So if we are wondering what is the shortest distance, we want to maybe look at the other case. So if we go here, or maybe closer here, or even closer here, we might get a shorter length. So let's call this C. Length of C. Does this go to 0? Why not? If it goes to 0, this would be a boring answer because minimum domain.
Epsilon.
It's epsilon, yeah. It is the linearization. So we get close to 0. So we actually are in the domain of the linearization around 0. And then the linearization tells us how long it takes to rotate half a circle. So length of C given by linearization at 0. So these kind of thoughts, how to kind of digest a phase portrait is, I think, very important to learn. Okay, so let's do that. Let's look at the linearization at 0 and see if we can get information about the rotational frequency there. Okay. Yeah, and we had the eigenvalues already. So linearization at 0, at 0, 0 has eigenvalues. Lambda 1 and 2 is plus or minus I, a root of mu divided by d. This is something we computed earlier, which I actually didn't compute, but I did tell you. You could compute it. And now we have to go back to our first year ODE class, how to write down the solution of a linear 2x2 system with complex eigenvalues. Who remembers? Sine and cosine. The answer is sine and cosine, right? So let's do that. So we can write, or a complex exponential. Yeah, right. Exactly. We can write the solution using sine and cosine. So as u of x and v of x, right? This is now two components, is like coefficient, and then we have cosine of this eigenvalue, root of mu divided by d x, and then we can have a phase shift phi and sine root of mu over dx plus a phase shift phi. Okay, long, long ago, when you were all young and enthusiastic mathematicians, you might have seen this somewhere. Or maybe not so long ago, I don't know. So this page, okay. Okay, so what do we do with this? Well, now we have a sine and cosine thing. And we are looking for this connection. So we start at an angle, what is this, pi half, and then we go to an angle minus pi half. So the offset would be pi over 2. And then for the length L, we want to do exactly a half a circle. So we want to cover the distance pi. Okay, so then for length L, we want this to be equal to the mu over d, no, mu, oh yeah, sorry. So if we sub in L into our sine and cosine function, we want this to be half a rotation, pi. That is the key. And then we can compute L from this super easily. So L is pi root of d divided by mu. And this is actually then, we call this L star, and this is our solution. So that's the minimum domain length. Wow, all of a sudden it was super easy. Right, using this explicit representation, doing half a turn, which is pi, and so we can just figure this out. So it is not 0. It has a well-defined value, and so it's proportional to the root of the diffusion. So if the diffusion is high, then the domain length has to be larger to maintain the population. And inversely proportional to the growth rate. So if the growth rate is high, you can get away with a smaller domain and still maintain a population. So this makes
Honestly, this formula reminds me of pendulum.
pendulum, yeah, right?
That's, but look at it, but
Well, it
the
is.
length of it, there is some.
So the linearization here, C, the linearization at 0 is the pendulum, the undamped pendulum. Yes, it is. So yeah, very good connection. Nice. Okay, so we have a little bit of time with the traveling wave thing.
I ask about the,
Yeah, can I ask the question?
remember the numerical simulations, there were other fancy boundary conditions like sponge layer and radiation condition.
Okay.
I'm reminded this because we're looking at a tumor
Mm-hmm.
and the domain. So radiation condition from the tumor outside is very relevant.
So the impact of the tumor to the outside of the
Or
domain, yeah.
The sponge layer
Yeah,
is a good blockage, so it's also relevant.
yes, of course, yeah. So then typically you wouldn't model these layers explicitly. So you would have a variable for the layer and the width of these layers and so on. Yeah, so that makes it much more complicated. Okay. So let's look, so I have half an hour, this is awesome. Let's now look at the traveling wave problem too. Which color didn't I use so much? Maybe purple, yeah. Okay, I should say for this L star, for instance, right here. Earlier I said there are two other formulations, like the stability at 0. So if you do a stability analysis of 0, you get the same L star. So this will work just the same. So we again look at Fisher KPP, duxx plus f of u. But now we are interested in the invasion. So how quickly does, for example, a cancer invade into healthy tissue? And so then we are looking at profiles of this sort. So here we call this a speed c. This would be u of xt, and here is space x. And we are interested in the speed c. How quickly does it go? So then the domain is infinity. Yeah. So we introduce a which oriented, sorry. Yeah. So we have assumptions on f. So typically we do it for the logistic type as well, but we can be a little bit more general here. So f at 0 equals f at 1 is 0. And second condition is f prime at 0 is positive, and f prime at 1 is negative. And the third condition is like a positivity larger than 0 for 0 less than u less than 1. So meaning f looks like this. It doesn't have to be logistic like a quadratic, but more or less logistic. That's good enough. Right. So now to describe this wave, this invasion wave, we introduce a traveling wave coordinate. Which I call z. Yeah, z is x minus ct. And I assume the solution only depends on z. So meaning I call this now phi of z is phi of x minus ct, but this is also u of x and t. So I assume my solution can be written as a function which depends only on one thing, no longer on two. And this is called a self-similar coordinates. And phi is called the wave profile. So the question is, can we find such a phi which works? And for phi we have boundary conditions. So as I plotted here, as we go for x to plus infinity, we want phi to be 0. Phi of plus infinity is 0, which means the population has not reached infinity yet. It is still invading. If we go to minus infinity, so where the wave comes from, we want to be at steady state. So on the left, going all the way to the left, we want to be at steady state. And the steady state is 1, which I assumed here in assumption number 1. F at 1 is 0. So that's the other steady state. So we are connecting two steady states by this curve. So now let's take this and sub it into our Fisher KPP equation right over there. So just follow my thoughts. So if you do the time derivative of this phi, you get an inner derivative minus c, right? If you do 2x derivatives, you just get 2 derivatives of phi. There's no inner derivative thing happening. So what we get is something like this. We get minus c phi prime equals d phi double prime plus f at phi, like this. And so again, this is a second order ODE, and we can do the same trick. We introduce something for the phi prime, and then we write this as a system of 2 equations. Insert page. Okay. So introduce. So good that we did the critical domain size problem already. So we use some ideas here. And then we get phi prime is psi, and psi prime is phi double prime. So we need to divide by a d at some point. So then we get minus c divided by d psi minus f of phi divided by d. So we get this. Okay, again, a 2-component ODE system. Yoo-hoo, which is nice, because we can do all our phase plane analysis stuff again. Good. So but first of all, I get rid of the d. I just want to rescale just quick. So c tilde is c over d, and f tilde is f over d. And then I remove the tilde. This sounds so incorrect, but this is done in so many papers, so I need to show this to you as well. So then the authors in a paper would just use just the same symbols and remove the d. And an unsuspecting student gets super confused. So so the idea is you rescale, but then you forget that you rescaled and you just continue. So let's call this number 2. Okay, so I need to plan this out a little bit. No, we can do this also. All right. So equilibria. So now we want to do a phi psi phase portrait thing. Let's look for equilibria or fixed points. And what do I find? I find 0, 0 and 1, 0. These are the 2 equilibria, so we can do Jacobian. And this time I write down the Jacobian. So here I get 0 and 1 minus f prime at 0 at phi and minus c. Right, so if we differentiate the first function by phi, you get 0. By psi, you get 1. Second, you differentiate by phi, you get f prime with a minus sign, and you go minus c. So that's Jacobian. And then if we sub in 0, 0, what do we get? We get 0, 1, f prime at 0, which is positive, so with the minus sign it's negative, and we get minus c. And so then the trace of j 0, 0 is minus c, and the determinant of j at 0, 0, this times this minus this times this is f prime at 0, which is positive. What does this mean? So trace negative, determinant positive. This means stable, right? It's a stable thing. It could be a node or it could be a spiral. This depends on the relative size of these terms. It's stable, node, or spiral. And to understand if it's a node or a spiral, we do need to look at the eigenvalues. And so we can compute them. Lambda 1, 2. And maybe I give you my favorite formula just once more, because this is so good. Plus minus 1/2 trace j square minus 4 that j. Okay, you sub in determinant, you sub in the trace square, all that, and we get minus c over 2 plus minus a half root of c square minus 4 f prime at 0. Okay, well, that's that. So now we can see where it changes between spiral and node, right? It is this root thing. If the root thing becomes imaginary or complex, then we get a spiral. So we have spiral for what? When c is small, right? For c square less than 4 f prime at 0, and a node for c square bigger than this. And this condition turns out will be important later. Yeah. Actually, we can already do that here. So we call the critical value c star just to be this 2 times root f prime at 0. I take the root, right, and then exactly where it switches from spiral to node, I call this c star. So let's look at the other fixed point now. I come back to c star after I have done the other fixed point. So j at 1, 0 turns out to be 0, 1 minus f prime at 1 and minus c. And then you can do the thing, etc., and we get a saddle point. So let's plot this out. Yeah. So we have phi and psi. We have a saddle point here at 1, something like this. And you can look at the eigenvectors, and they go in and out like this. And then we have 0, which is either a node or a spiral. So I need 2 pictures. So coming out, going in, again, this is phi, and this is psi, and or a spiral. So if it's a node, it's a node. So then it looks like this, going in. Actually, if you do the linearization and compute the eigenvectors, you find that the node is actually oriented like this. So the 2 stable directions are in the same quadrant. But it's still a node. For the spiral, it looks like this. It goes in. Now, what were we looking for? So this is phi and psi. You remember in the critical domain size problem, I now looked at the boundary conditions and I tried to fit the boundary condition in this phase portrait. So I need to do the same here. What were the boundary conditions? This was phi at plus infinity is 0 and phi at minus infinity is 1. Where are these solutions in the phase portrait? So phi at plus infinity is 0. So we need an orbit which converges into 0, right? And luckily, in both our cases, 0 is stable. So whichever of these orbits here I choose, I will converge to 0 as t goes to infinity. Okay? So so the red one could be 1, and here the red one could be another one for the spiral case. These are orbits which forward go to 0. Nice. Now backwards, they have to come from 1, right? As phi goes as x goes to minus infinity, we need to come out of here. So then it can only be this one or this one. Because one is a saddle. These are the only two possibilities. So this one or this one. And now somebody has to be bold and say, why don't you make a connection? Right? So it looks very natural that you maybe have a connection here, there, or maybe you have a connection here to this guy. So these are the solutions we are looking for. And so then we need to show they exist. And this can be done. This is an involved proof, which I will not go through today. But I should give you a reference. Okay, but do one after the other. So, yeah. So let's call this connection, let's call this maybe 1A. What do I want to call it? Let's call this connection little a, and this connection little b. Now there's a problem. B is not good. Why is B not good? Because of negative. So phi again describes the wave profile, so it describes the, let's say, cancer cell distribution. And here phi is negative. So even if this connection exists, it is not a solution to our problem because we cannot have negative solutions. So B is excluded. But wait. When did B happen? B happened here. The spiral case. So this was the B case. This was the A case. This happened when C is less than C star. So we find a critical speed, C star, and if I'm below C star, I cannot have a solution. Ah, right. So then C less than C star is not possible. So we find a minimum. So C star is something like the minimal possible speed, maybe. So what is missing then still maybe to show that A exists. So we still need to show that the connection, as I dashed here in A, that this can be really made, that the phase plane has these connections. You can do this numerically, you find it very easily, or you use the method of. And now I need to find Hillen, I think Hillen. Don't I have the thing here? No, I don't. Yeah, so in my notes, this page, this proof is like 8 pages long or so. Okay, so let's say 8 pages in my notes. If you're interested, I can post it anyways. I think original proof by Hillen. Yeah, and I don't have time to go through it in detail, but I give you one thing, one idea to do this. So here we have the orbit we are starting with, and we want to end up at 0. So we want to get to one of these two, and we get to the lower branch. And what we do is we build an invariant triangle like this. And this. So let's call this a delta. It's an invariant triangle. Which means you need to show that the flux is always inside. So here we go inside, and here we go inside. And here we go inside. And then the only exit of this triangle would be the point 0. So we need to show the flux on all these side conditions. And then we can use Poincaré-Bendixson to prove that we have to converge to the center in the triangle and Poincaré-Bendixson. Okay. Yeah, so I leave it at that. Maybe I post my notes and then you can go through this in detail as you like. But then the result is actually our C star. So let me summarize this on the last page here. Insert page, annotate. So the minimal speed invasion speed is this. C star is 2 f prime at 0. And remember, we set d equal to 0 early on, and so on. But so we can reverse this. Or if d is included, we have C star is 2 root d f prime at 0. And this is also called the Fisher speed. And that's it. So this is everything I wanted to cover today. You did well. I did well. We all did well. Awesome. So other questions?
The only point of escape is 0.
Yeah.
Is it because multiple solutions are out there?
Well, there are multiple solutions going into 0. That's right.
But that escape of flux from the region
Yeah.
happens because of the ambiguity, which solution to take. So that's escape.
I see.
Say, I
Yeah.
don't know which one to take, so I'm out.
But it's also not escaping because it takes infinite time to get there, right? So you kind of approach 0, but it still takes t to infinity to really get there.
It's only theoretical.
Yeah, yeah. Good. Thank you.